PhD scholar from NMCAD Lab, working on the analysis and design of composites and metamaterials to tailor their electromagnetic energy absorption and buckling strength capabilities for stealth applications. Prior to this, he did his master's from IIT Madras, which included a project from Leibniz University, Hanover in Germany.
Thanks for the introduction. So today I will be covering two topics. One is the collaborative work which we're having with Professor Bisani, and the other topic which I've worked till now in my PhD. So starting with the auxetic materials, we are working on the evaluation of absorption capabilities of auxetic materials. So these are the contents which I'll be going through. So starting with stealth, stealth is defined as a covert or concealed movement under different detection techniques. So one of the widely used technique is faceted structure, where the aircraft will be having multiple faces, which we can see here. So once the radar sends the waves towards the aircraft, in the case of passenger aircraft, because of the rounded surfaces, the waves will be reflected back towards the source radar. But when we have this kind of faceted structure, these waves will be reflected away from the aircraft so that the detection will be becoming difficult. So the other widely used technology is radiation absorbent materials. So in the case of faceted structure, even though it has a faceted structure, it's not just a single radar. We'll be having multiple radars. So if not the source radar, some other radar can detect these reflected away waves. So by using these radiation absorbent materials on the top of the skin of the aircraft, we can further reduce this detection of the air. So currently I'm working on developing these radiation absorbent materials using composites as well as the metamaterials. So the quantitative measure of this stealth is measured using the radar cross-sectional value. In this image, you can see for Airbus A380, which is a passenger aircraft, the RCS value is around 100 meters square, whereas for F117, it is 0.003 meters square. So you can see how much difference you will be seeing in the radar when we use a stealth aircraft compared to the passenger aircraft. So currently, India is developing its indigenous stealth aircraft, which is Advanced Medium Compact Aircraft, which was developing by HAL. So it is under process, and within few years we will be able to visualize the stealth aircraft for India. So currently, the history and the current scenario on these radiation absorbent materials, which I'm going to talk now. So the work on this radiation absorbent material started back in 1930s. During World War II, Germans were able to practically develop these radiation absorbent materials for marine applications. And later from 1980s, different carbon-based materials are being used for these radiation absorbent applications. But one of the problems with carbon-based composites for stealth applications is the narrowband absorption capabilities. We have to tailor the properties at microstructural level so that we can have broadband absorption. But when it comes to metamaterials, there are multiple research works which have been published where by using different metamaterials, they were able to obtain broadband absorption. So currently the research was on these radiation absorbent materials are focusing towards metamaterials from the composites. So that was the idea behind working on these auxetic materials for their absorption capabilities. So I'll be citing some 2 or 3 research works on these auxetic materials where they have talked about this absorption capability. So this was the first research paper which caught my eye and dragged me towards working on these auxetics for absorption capabilities. So in this paper, they have presented their experimental and numerical works where they have identified a linear relationship between electrical permittivity and the Poisson's ratio of the material. So basically, the auxetics will have a negative Poisson's ratio. So because of this negative Poisson's ratio, they will have better buckling strength compared to the conventional materials. So that was the basic idea behind going for auxetics. So it's not just the strength, we are also interested in absorption capabilities as well, which we can obtain using the electrical permittivity. So we have seen that there is a linear correlation between these two things. So we can easily obtain both the strength and absorption capabilities. So that was the basic idea behind going for auxetic material. And this was one of the numerical analysis which was done on auxetic honeycomb structure, where they have varied the geometrical parameters which are involved for different structures of this structure, and they have obtained absorption spectra across the frequency ranges. But one of the drawbacks which I have observed in this research work is the thickness of the sample was around 20 mm. So it is not a feasible thickness for aircraft structures if you want to use this kind of structures. So the basic idea was to reduce this thickness so that we can implement for aircraft structures. So that was also one of the motivations for me. And now with the advancement in manufacturing technologies, polyurethane foam composite has been applied with triaxial compression for obtaining the auxetic kind of composite material. So it's just not the using metals or ceramics, they were also going for using composites for getting this auxetic structure. So here they have obtained different auxetic configurations, and they have evaluated the absorption spectra for different configurations of the composite. So now we come into the research gap. I've identified that only few auxetic geometries have been studied for their absorption capabilities, and the incident angle is also restricted to normal incidents. But in the case of radars, if we want to use it for stealth aircraft, we'll be having like multiple incident angles which will be sent onto the aircraft. So we should see whether it is feasible to have across incident angles that are possibly incident on the material of interest. And mostly the materials which they have studied for auxetics are metal-based ones, and we are interested in ceramic-based auxetic materials because it's just not the electromagnetic absorption. There is also IR signature capture, which is going to happen when it comes to stealth. So by using ceramic-based materials, we can trap the heat energy and we can reduce the IR signature as well. So these are the two multi-objective functions which we want to achieve using ceramic-based auxetic materials for stealth applications. So this was the motivation, as I was talking previously. It's not the absorption, but also the strength which we're interested in. Because of the negative Poisson's ratio of these auxetic materials, we can obtain better buckling strength compared to the conventional materials. And we're also interested in reducing the IR signature, just not the electromagnetic absorption. So this was the objective. So to examine the influence of geometrical configuration on the ceramic-based auxetic materials in X-band frequency range under different incident angles. So this was the methodology. So, but these properties are going to vary across the frequencies when we work at gigahertz range frequencies. So initially we needed the experimental data from the literature works, where we have extracted the properties from the literature works, and then we have selected the different auxetic geometries we are interested in, and then we have developed a tool to obtain the effective properties, as we wanted to tailor the geometric configurations of these auxetic materials. Then we have used the transfer matrix method for the anisotropic material which we are working on for obtaining the absorption spectrum. So this is Liu et al.'s paper, where I've taken the frequency dependent properties of electrical permittivity and magnetical permeability values across the X-band frequency range. And these are the 4 different auxetic geometries which we have considered in our study, which is star, reentrant, anti-tetrachiral, and missing grip geometries. So this was the tool which I'm talking about. So this was already established methodology for RUCs, which is representative unit cells with a single fiber, but we have modified it for auxetic materials for obtaining the homogenized properties, so that there is no need to deal with this complex structure. We can replace the complex structure with a homogenized material, which behaves similar to the unit cell which we're dealing with. So this was the I'm not going into the complete formulation of it. I was just showing you the flow chart of it. So you'll obtain the energy functional for the defined problem. And there are fluctuations when it compared to the macroscopic scale and microscopic scale. Those are the unknowns for us, which we want to evaluate. We will do the minimization problem and we will obtain those fluctuations. And then we obtain the homogeneous energy function, from which we can obtain the effective properties tensor. So this is a magneto-electroelastic material. So the computational time it takes when we go for finite element based homogenization technique is very huge. So it might go into hours if you want to calculate for one single case. Here I have like 15 different frequencies where I have to evaluate, and 4 different properties which I have to evaluate. So by using VAM based homogenization, we will be able to do it within say 1 hour for all the different cases which we have taken. So this is one of the attractive features which we have found from the tool which we have developed. And then the transfer matrix method. So this was also an established method for isotropic materials. We have extended it for anisotropic materials, which we have barium titanate and cobalt ferrite materials, which we are interested in. And here also, I'm not going to bore you with all the equations here. So by using Maxwell's and constitutive equations, we will be getting some normalized equations. So here you can see these are the partial differential equations, 6 partial differential equations. We will further reduce it using transfer matrix method, which will be applicable only for homogeneous. As we have already homogenized our material, this assumption will be perfectly valid for using this transfer matrix method. So we can reduce it to second order differential equation. From 6 partial differential equations, we can reduce it to two second order differential equations, which we further solve for obtaining the fields, both the electric field and magnetic field, where this physically means where W's and V's are the modes in which it is propagating, and decay and the loss or gain of the field can be obtained using from these parameters, and C represents the amplitude of those fields. So this was the material which we are interested in, and let's say we have two different mediums on both sides of the material. We'll be applying the boundary conditions at those two interfaces, so that we can obtain the relationship between incident amplitude and transmitted and reflected amplitudes. So the matrix which relates these things is called a scattering matrix. Even in the regular experiments also we will come across this scattering matrix. So we can experimentally validate these results once we have this formulation with us. So we have 3 layers. Actually, I was talking about reducing the thickness of the material, right? So what we are planning to in the conventional metamaterials, what they will be doing is they will have a unit structure, and they will be having a dielectric substrate in the bottom of the material, and then there will be a metal backing of it. In this way, they will be able to increase the absorption capabilities and reduce the thickness. So that is the same strategy which we are using here. We have the auxetic material in orange, and then the dielectric substrate and the metal backing. This helps us to reduce the thickness to almost 2.5 mm. Previously, they have presented for 20 mm. We are able to reduce it for 2.5 mm, and we can get like better absorption capabilities, which I will be showing in my result section. So for individual layers, we will be obtaining the scattering matrices. Then by using Redhofer star product, we can eliminate the interface relationship, and we can obtain the global scattering matrix. So this will be used for obtaining the amplitudes in reflection, transmission, and absorption coefficients, and in the final we can obtain the reflection and transmission coefficients for our desired material. So these are the absorption graphs. So here you can see for anti-tetrahedral geometry, we have varied the thickness of the sample from 1.5 mm to 2.5 mm. With the increase in the thickness, we can see the peak of absorption is being shifted towards the left. So this phenomena is called as quarter wavelength phenomena, which is very well established in electromagnetism domain. So similarly, for star also we have done the same analysis, and for other geometries as well, like reentrant geometry as well. And then we have compared across the geometries. That was one of the objectives. We wanted to evaluate which geometry is more capable for our application. So we have identified that star geometry is having better absorption capabilities, even though we increase the thickness of the sample. And one more interesting observation we have made is both the star and missing group has similar absorption spectra. For validating this reason, we evaluated the impedance. It is kind of resistance of movement of electromagnetic waves through the material. We have identified that resistance is similar for both the structures. So that is the reason why we are able to obtain similar absorption. Now, by varying the incident angle, this is also one of the other objectives which we wanted to identify. So with the incident angle increase, we can see the graph is shifting towards the right direction. This is if we resolve the angle of the effective thickness value, if we evaluate, it is going to reduce it actually. So previously we have seen with increasing thickness, it is lifting towards left. When we increase the incident angle, it is nothing but the effective thickness through which the waves are passing are decreasing. So that is why we are seeing a shifting towards the right direction. So with the cross-sectional area, there is not much variation in the absorption spectra. It is the resonance which depends only on the geometrical parameters, but not on the effective cross-sectional area of the material. Then we have validated our with the numerical analysis, which is frequency domain, finite difference frequency domain analysis in commercially available CST Studio Suite. These were the star geometry which I have considered, and there is very well agreement between these two methods. So there is hardly 2-3% error with the analytical formulation which we have worked on and the finite difference frequency domain method. So this completes my talk on absorption capabilities. Now, as I was talking previously, we are interested both on the strength as well as the absorption capabilities. So next comes the topic which we are collaborating with TUDERT, where we are interested in evaluating the buckling strength of the material. As I was talking, like we are interested in using this auxetic material on the skin, where the buckling strength is the primary failure criteria. So starting with this formulation of VAM, we wanted to, as we have the experimental data from TUDERT, we wanted to validate our methodology using their data so that we will be confident enough of use the same methodology for our desired auxetic structure. So that was the idea behind having this collaboration and integrating my PhD formulation. So why do we need an additional stiffener? That was the first question which came to my mind. I thought of sharing the same. So we have used the same VAM formulation which we have developed for when we have a same plate without stiffener and with stiffener. We have seen that 20% reduction in displacement has been observed by having a stiffener along with the plate. So this was to show like why do we need a stiffener? Why can't I just go with just the auxetic structure? Why do we need an additional stiffener to that? So then comes the stage one where we wanted to develop the VAM formulation for the composite panel with the stiffener and validate it with 3D finite and experimental works. Then comes the stage two, which I was talking about, where we wanted to design a material for broadband absorption and use the same formulation for obtaining the buckling strength. Once we validate the formulation here, we can go for using the same formulation for our desired auxetic material for obtaining its buckling strength as well. So this was the flow chart. So in the VAM, we will be for the plate analysis, we will divide it into through the thickness analysis and 2D nonlinear analysis. So in the through the thickness analysis, we will be obtaining warpings. Warpings are the main unknowns for us. So those are the warpings which we will be obtaining from through the thickness analysis. And we will also obtain the 2D constitutive law from through the thickness analysis. These are the two outputs which we'll be getting from through the thickness analysis of VAM. So then we will be using the 3D recovery relationships from which we can obtain the constraint matrix. This constraint matrix helps us to obtain the continuity between the plate and the strange. So that is where this constraint matrix plays a role. So these two will be the inputs for us for 2D nonlinear analysis. So this 2D nonlinear analysis will give us 2D displacement, strains, and curvatures. And again, we'll go back for the 3D recovery relationships for obtaining the 3D displacements. So this was the flowchart for our current VAM formulation. So I'll be starting with 1D through the thickness analysis. So in the through the thickness analysis, so there is some geometrical configurations which are involved before going into this, but I was skipping that part. So we will be obtaining green strains from the deformation gradient tensor. Then we will obtain the strain energy density using these green strains. Then we will be integrating it through the thickness so that we can get the cross-sectional strain energy density, which will be differentiated for obtaining the stiffness. So there are two other constraints which comes for warpings. This helps us to reduce the rigid body motions of the normal in the deformed configuration. So that is where these constraints are going to play a role. Then we will be obtaining the potential energy functional. So the name of VAM comes from here, the variational statement, where we minimize the potential energy function, which combines the constraints and the strain energy density which we have. So that from there it comes the variational statement. So we will be obtaining some Euler-Lagrange equations which we want to solve for obtaining the unknown warping functions, which I was talking in the flowchart. So then once we double derive the potential energy functional, we'll obtain through the thickness 2D constitutive law. Then the second part where asymptotically, which we're talking about variation asymptotic. So there will be small parameters which will be identifying from the kind of analysis which we are doing it. Here we are considering the plate analysis. So in the plate, we have thickness to length ratio as one of the small parameter and the strains as the other small parameters. Once we incorporate these ordering of these small parameters into the energy functional, we can divide the energy into multiple orders. So this is the 0th order, first order, and second order. So most of the contribution of energy comes from the 0th order, and next contribution comes from the first order. So this is how the ordering of the energy terms will come into place. That is why we will be calling it as asymptotic method, where in 0th order we'll be considering only the highest contribution of energy of pi 0. Then we'll be considering pi 1 as well in the first order analysis. So in this, I'm going to show only the 0th order analysis results. So yeah, Xavier has shared all these details previously, the properties and the orientation. We're considering the same details here. So the skin is of 8 layers laminate and stringer is 7 layers laminate. And through the thickness analysis provides us 2D constitutive law. So these are the stiffness matrices which will be obtaining from through the thickness analysis, which depends only on the thickness of the laminate. Here I'm showing only for skin. Similar analysis has been done for the stringer as well. So this was the main part of the present analysis, which is the constraint method, where we wanted to ensure the continuity at the interfaces. So Once we obtain the stiffness of this element, then the K2 will be different because of the inclination angle with the reference surface, and K3 will also be different because of the inclination with the reference surface. So we will be having 3 different kinds of stiffness for individual elements. Then we wanted to ensure the continuity at the interfaces of different elements. So that can be done using this 3D displacement recovery. So this was the 3D displacements. These are 2D displacements, 2D rotations, and the warping functions. So once we ensure the continuity at the interface of all the nodes involved there, we can obtain a continuity relationship between the displacements of member 1 at the interface nodes and the member 2 at the interface nodes. This gives us the constraint matrix. This was the constraint matrix which relates the continuity condition of 2D displacements of member 1 and the member. Similarly, for other members also, we will be obtaining the continuity, which is x23, x34, and x45. So this will be the whole constraint matrix for the stiffener alone. So using this constraint matrix, we can obtain the overall stiffness of the material. Then comes the constraint between the plate and the stringer. So here also similarly, we'll be having the common nodes between the stringer and plate, from where we will be obtaining the XSP, which is the constraint matrix, which helps us to relate the 2D displacements of stringer and the plate. Similarly, we obtain the final stiffness. This will give the stiffness of whole structure, which we are interested in. Now we'll be going to use the 2D nonlinear analysis, where I've used a modified Raphson method for obtaining the load response characteristic. So this was the 3D finite element analysis which Javier has presented in the morning, and these are the results which were obtained from zeroth order VAM analysis, and we can see that there is a very close relationship between these two analyses. The error was around 5%. I haven't done the buckling analysis. This was just the load response characteristics. Still, we are evaluating the buckling shape of different modes, and this was with teflon. The teflon is of 40 mm, which was placed in between the stringer and the plate, where the error percentage was little higher. But once we go for first order VAM analysis, we are sure like we can further reduce this error. Now comes to the one of the main thing which we take away from VAM is the computational time it takes. Here I'm doing a dynamic implicit analysis, static load. I'm not going for the buckling. I'm just applying the compressive load at this part, and the nodes are constrained here. And we can see that when the load is 25.2 kilonewtons, we can see that almost 80% reduction in the time has been observed. So till now, I was talking about the plate, right? Where we are replacing the 3D stringer with a 2D stringer. But in the further analysis, we wanted to replace the stringers with a single 1D beam so that we can further reduce this computational time. And one more thing I forgot to mention is here you can see the ordering was same for both the analysis, but this is for a single stringer plate element. But if we go for multiple stringers, we can appreciate more the VAM compared to the Abacus 3D finite element analysis. So that was also one of the ideas which we have when we go for multiple stringers. We wanted to see how much efficient the VAM is compared to the Abacus computational. So these are the references, and thank you. Any questions from the audience?
So are you planning now to do for the part that we are working together?
Yes.
So the backend analysis,
yes,
and compare with the hour?
Yeah.
But there was a little bit of discussion about teflon, not teflon, and so on. So you were able to put inside the
Yeah. We were able to.
Okay. So how you introduce the teflon?
So we have disconnected the connectivity at that region of 40 mm between the node connection was detached from there, but we haven't incorporated the damage initiation thing. Yeah, damage initiation is not yet incorporated. Without,
Are you planning?
Yeah, we are planning to incorporate the damage initiation as well, because that was the main thing, maybe because it takes like days, I think. Yeah.
And how have you already thought how to?
No. I were able to start that. Yeah.
Right. Yeah.
So with that method, you can get the displacement and the load.
Yeah.
But can you get like stresses at any point?
Yeah. We can obtain the stresses as well. Yeah, we can do the recovery of stresses as well.
And there's a key for getting the
the
delamination.
Yeah, delamination. This is just the preliminary results. Like 15-20 days I was working on this. Yeah.
And when you get that response, Do you lose stiffness due to buckling, or is just a straight linear response?
Yeah, it was linear actually because the 2D stiffness which we are getting is a constant one. Once we go for first order analysis, we can see that nonlinearity coming into place. Yeah.
Some questions? It's actually, this is kind of a major breakthrough. We've been trying this for a long time with many other students, and it's not been successful. And finally, Phanendra could achieve that in a fairly short amount of time. Considering the pressure of this workshop, you wanted to get some results in place, and he's been able to achieve that. There's been a lot of work on VAP that has been done on beams separately, on plates separately, but on stiffened plates, this is something entirely new. And also because initially the data we got was with teflon. So he took up that challenge of doing it with the teflon in place as well. So it's really exciting in terms of the next steps, especially in terms of determining the buckling load and the nonlinear behavior and also the damage initiation. I think it's going to be a really, really fruitful effort. So thanks for instigating that, because the work that you had set up a challenge for him, which he was up to the mark.
Yeah, definitely.
You could be judged for his PhD as well.
Yeah, it can.
Yeah, this was a very, very interesting connect that we brought about, because seemingly they were like apples and oranges, but there's a very good blend now.
Can discuss and be a more.
Yeah,
More
Sure.
right now.
Sure.
Any question?
yeah.
Take advantage of.
Yeah. Sure.
Here.
So while we clap for him, not only for this talk and his work, but also for leading this whole workshop as the team of volunteers. So not only for Shanika, but also all the other. So